questions up to this point? Other than what? I wouldn't tell you if I did. Nothing personal.
I don't want to ask this, but are we doing that third quiz?
Yeah, I should put a third quiz up there just because I know some people have probably been banking on it, hoping for it. So,
Do we have one more do today?
yeah. So I think I'm going to do a third quiz maybe sometime that last week. And it'll be kind of a practice for the newer stuff on the exam. I'm not going to do another homework today, though, because we don't have a class next week, so I think I'm going to give you a homework on Monday, which will be due a week from Monday. And we'll hopefully cover graphs and some more trees. All right, any other homeworks coming in? So general comment, if you have questions, you should feel free to ask them during class. Like when I say, are there any questions? But if questions come up along the way, you can always, right? Even if it's not directly on topic, if you remember something, put your hand up. When I get to a breaking point, I'll call you and say, hey, I forgot to ask on the homework, what did you mean by such and such? That kind of stuff. As opposed to everybody rushing up at the end of class saying, can I ask you about such and such? Because then I get slammed between classes. And I'd rather spend class time and answer these questions in front of everybody else so that we can all benefit from it. Unless it's something you've got to ask personally, right? Like, I can't take the final exam on that date or something like that. All right, let me.
I actually do have a question.
No questions. No, what?
On the third question.
Mm-hmm.
They wanted a discussion there.
Yeah.
Do that? I mean, what I put down is that the thing's going to go through one of the branches entirely.
Mm-hmm.
It's going to do that all the way through, unless the same data point is in either side somehow.
Mm-hmm.
But on the other side, if the data point is there, then it's going to go down to that point, but it's going to do every other branch above that point.
Mm-hmm.
So, at most, a total of n tries in terms of the number of nodes.
Yeah, I think I wrote that algorithm deliberately inefficiently.
It was pretty bad.
Because the farther right it is in the tree, the longer it's going to take. So always search left first.
Yeah.
I think. Yeah.
Well, it kind of searches both at the same time. There's really no decision making. So first it's going to go to 2 nodes. The node that's going to go to 4, then 8, then...
Yeah, it searches both branches entirely.
Right, so it searches before it checks the return value. So even if what we're looking for is, let me see, did I even bother checking the root before I searched?
Yes, you did.
Yeah.
Okay,
Yeah.
so if we're looking for this, it's going to search this whole tree, and then it's going to search this whole tree, and then it's going to say, did I find the data?
But it's not searching the left tree once it hits the node, I thought. Because I thought there was a thing
If
where
my node's up
you
here...
had like if the root equals this, return true,
Yes.
so that stops searching further down.
Yes.
Right. But if you're at a leaf node, it's going to search that and search that, which means it'll search that and it'll find it. But it'll search this and this, and then it'll do the same thing over here, and it'll search those.
It'll also search the other leaf node right next to the one that's that one.
Right, it'll check left and right, but it won't descend beyond this one. So,
Right.
So if your node is a leaf node, it's going to search every single node.
So I would say it takes the time it takes to search n nodes at the maximum and half the nodes, or all the nodes in the other branch at a minimum.
Well, if the information thing that you're looking for is the root, it's just going to find the root and go, hey, we're done.
Yeah,
Okay,
so
so that is
root,
the absolute minimum. That only happens if the absolute root node of the entire tree happens to happen.
Right.
Anywhere else, it has to search the entire other than half the tree.
right, so there's root.
You're right, though. I didn't consider
Let's
that.
call this B and C. If it's B, it's not going to have to traverse this, right, because it'll find the root, but it will traverse the whole right side. So that's roughly n over 2, what we'll eventually call order n over 2,
Assuming it's balanced,
assuming it's balanced,
which I
yeah.
guess is given. Is it given? It's not
No.
necessarily given. No.
But things only get worse if it unbalances. And if it's at a level of 2, so this is level 0, level 1. If it's at level 2, it will search this whole thing and it will search this whole thing. And it will stop searching here, so it'll be, I don't know, 3/4 in or something like that. Statistically, what level are you most likely to find your node at? Yeah, it's most likely to be, well, it's as likely to be a leaf as not a leaf. Because half of your nodes are leaf nodes
In a balance.
in a balanced tree, and 3/4 of them are on the 2 lowest levels.
More than half,
And so you're most likely to find it pretty deep in the tree. So your time's going to tend to be roughly on par with the number of nodes. And when we formalize order of complexity, we'll see order n over 2 is exactly the same as order n in terms of how horrible the performance is.
So, if you were designing an algorithm to find these things, how would you build it so that it tries to check the leaf nodes first? Without...
If you wanted this to be more efficient, rather than checking the leaf nodes directly, you do what I think Yosha suggested when I first put this on the board. Compare the data to the root and either search the left or the right subtree.
Right,
depending on whether
so
it's
actually
less or
follow the
greater.
path.
To actually follow the path.
And you get log time for that.
And that cuts you down to log 2 of n.
Yeah.
Because now you're just descending and it's the height of the tree that governs how many operations.
On the L1,
Mhm.
what's that symbol? In front of the in-halves?
Yeah,
This,
I think that's an ampersand.
that's an O.
Oh, sorry. That.
It's a script O.
Crypto?
We haven't talked about order of complexity yet. Well, we've used the term, but we haven't formalized it. But it's a way to measure how complex an algorithm is in terms of time. And it's aiming to characterize the difference between, say, searching an array with n elements roughly takes you n over 2 operations, depending on where the thing is in your array. Sorting an array with n elements, if you do a bubble sort, takes roughly n squared operations. Searching for something in an array that's sorted takes you roughly log n operations, because you can play high-low, you keep dividing your array in half. And what these mean, order n means if I double the size of my array, I basically double the time it's going to take to perform this task. Order n squared means if I double the size of my array, my time goes up by 4x. If I make my array 100 times bigger, my time goes up by 100 squared, 10,000. If my array is 1,000,000 times bigger, this goes up by 1,000,000,000,000. Whereas here, if my array is 1,000,000 times bigger, my time goes up by only 1,000,000. Here, if my array is 1,000,000 times bigger, my time goes up by 20. So it's a way to sort of get a handle on how the complexity of your problem grows as the problem size grows. How does the time complexity increase?
Operation of log 2 then.
Yeah.
And all that. So we'll be talking more about that in data structure.
We'll talk about it in data structures. I may talk about it a little next week, although I just talked about it. And when you get things like, right, then you just kind of like roll your head and roll your eyes and
Strong argument for an algorithm.
say what? Yeah, look for a different algorithm. On the other hand, when you get an algorithm like this, order 1, right, that's great.
You're doing something right.
Yeah, you get 1,000,000 times the data, it takes the same amount of time to process it as it did 1,000,000th of data.
What would fall into that category?
Hashing,
Oh, that makes sense.
right, if it's an ideal hash, the time it takes to find something is fixed regardless of how much data you're looking through. That's really cool.
We even have that. That doesn't. Because you still have to, like, if you've got a file of n bytes,
Mm-hmm.
it's got to go through the whole file, doesn't
Nope.
it? No.
With a hash, you take the thing you're looking for and you run it through a function that tells you where that's stored in your file.
Oh,
And you just go and you get it from that one spot.
I see what you mean. So hash lookups, you mean?
Yeah.
Okay. So, yeah.
I remember hearing these are common interview questions they'll ask. Like, what's the like, operation of the binary search tree?
Yeah.
Oh, dog 1 or dog 2, and what is the correct answer?
Yeah, so these are good ways to characterize things like sorts and searches and other types of things we do with data structures, bless you. And you can use them when you're trying to choose, right? Do I want to do a bubble sort? Do I want to do a merge sort? Do I want to use a hash? Those kinds of things. So yeah, I can believe they pop up in interview questions. There's no telling what pops up in interview questions. So.
I did mention in my answer on this one that this one would be fine for a small tree just because it's simple to read. I mean,
Yeah.
you can hatch that out in about maybe 5 minutes. You've never done before. We've only done it a few times.
Yeah.
You know, when you have 100 nodes,
Mm-hmm.
you start to see a little bit of difference.
Right, right. And like I've said, I always do a bubble sort just because it's the quickest for me to code, and if I need something more sophisticated, I just get a sorter from somewhere. So when I'm coding a sort, it's probably a bubble sort.
That's what libraries are for.
Yeah, that's what libraries are for. All right, do you want to run through the homework questions since we're talking about homework anyway? So that data that was coming in, all right, so it was D, W, B, E, G, F, C, H, Z, Q, A. So if your data arrives in that order and you're building a binary search tree the way we described, the first piece comes in, that's got to be the root. And then each piece that comes in after that, you just move left, right until you get to a spot where there's no node and you insert it. So W is going to go to the right. B will come to the left of D. E is bigger than D, less than W. G is bigger than D, less than W, bigger than G. So it comes down there. E, F is bigger than E, less than G, so there's your F. C is less than D, bigger than C. H comes here, G bigger than H. H is bigger than G. Z comes to the right of W. Q is less than this, bigger than G, H. There's Q. And then A, smaller than D, smaller than B. So that's your tree that you would get just from building it without any balancing or anything. And then node left, right. So you visit the root first. So you get your D. And then you come down to the left, visit the root, and then go left, right. And then we traverse the right subtree, so W is the root, come to the left, there's an E, come to the left, and then to the right, there's a G, left, and then right subtree, HQ. And then we pop all the way back to the W, and we traverse the right subtree. So if I didn't skip any steps, that's the pre-order traversal. The in order should be A, B, C, D, and then come down here, traverse this in order F, G, H, Q, pop back up to the E, pop back up to the root, and then the right child. I should write these down so I don't have to do them again tonight. So left, right node, left, left, left gets you to A, and then C, and then the node, that's the left subtree. Traverse the right subtree, go left. That's as far as we can go. Traverse the left, traverse the right. So hit this subtree, which says go left. And then traverse this, which will go left and then right. And then pop back to the H. Then the root of this tree is G. And then the root of that tree at E. And that's the whole left tree. Then traverse the right tree. And then go W, and then finally the root of the whole tree. Does that look familiar?
The first and second one, the first and third ones just seem so unintuitive in the way
Yeah.
you path through the tree.
It took far more effort than it really should have to do that.
It
It's
feels
just
like it feels like in this problem, the first and the third, the pre-order and post-order are just not helpful.
Yeah, except postfix is useful for parsing.
I
Yeah,
thought it was asking LNR to be in that order, so
you what?
I thought it was asking my LNR to be in the order it was written in.
In this order?
Yeah, so
Oh.
it's all messed up.
Did you build a tree so that the LNR would come out like this?
Yeah.
Oh, well, that's pretty cool.
That is nifty.
Yeah. I'll have to see what your tree looks like. Yeah, that's cool.
We were talking a while ago when we first got into trees about the different orders being for doing different operations on the tree.
Mm-hmm.
And there was, I think LRN was the one that we didn't have. We didn't know what it was supposed to do. I found out it's for deleting the tree or deleting nodes.
Oh, really?
LRN.
Oh, because it gets you to the edges of the tree. Oh,
That could make sense.
is that where you're not left with any?
So when you want to delete a node, you need to find like either the biggest node in the left subtree or the smallest node in the right subtree. So yeah, those would help you find that one.
That's cool.
So if I want to delete the D, I could find the biggest node over here and promote it to the root, or find the smallest node over here, which is E, and promote that to the root.
Either of those would work.
Either of those would work, yeah. And sometimes you do a balance analysis and decide which side to take it from, or sometimes you just alternate to try to minimize the unbalancing.
That makes sense. That's nifty.
Yeah, we get to code that in 222. We'll actually like take data in and build up trees and insert and delete and stuff like that. And it's a lot of fun, actually. I don't mean that sarcastically. It is fun. All right, any other questions about trees, homework, life, universe?
We have more to go over, right? More.
Yeah,
This.
Oh, do you want to go over the others?
I guess you go over all of them.
Okay. We can do that.
Because as far as the tree stuff goes, I was mostly interested in the balancing portion.
Okay.
'Cause I mean-
So level of each node, right? Level starts at 0, 1, 2, 3, 4, 5.
Started at 1, 2.
Okay.
Or you start at 1. So
Okay.
Does it matter if it starts at 1 or 0?
technically it starts at 0, and that makes other things work out.
Yeah.
So because it's the number of edges from the root to a node.
Which is weird because
Look
I
at the
didn't
height.
find it noted in the book, and
Yeah.
when I looked online, it said that the level is paths from root plus 1, which would make the root 1.
Okay, that might be a standard. That's fine.
It essentially comes down to how programmers count versus where your people count.
Yeah, that also makes the height of an empty tree 0 instead of negative, which.
But the funny thing is that mathematicians came out with this. So how do they do it? Do they start with 2 or something?
That's a good question. All right, so height of the tree is just whatever the maximum level is. So 5 if you did this, 6 if you started from 1. And a balanced tree that has the same in-order traversal. How many nodes do we have?
11.
We've got 11. So,
I
don't
found
know.
convenient,
Yeah.
which I found convenient.
Let's
Yeah.
pick the middle. Let this one
Yeah.
there.
Yeah.
I sorted them alphabetically,
Yep.
so basically LNR. You take the middle one,
That's what
and then
That's your
you
root.
split the two
Yeah.
on the sides into 2 separate things, and then you get the middle of those 2 new lists, and put those on the sides, and so on and so on.
Yeah.
Yeah. Now, I have no idea if that's the real way that you do this. Probably not, but
Yeah,
this worked out pretty nice.
especially since it requires actually sorting the thing, which
Right.
might
It's
be.
kind of,
On the other
since
hand,
you're making a sort tree, though.
on the other hand, LNR would just spit out a sorted version, so.
Yeah, L&R will always be sorted as long as we put smaller things on the left, bigger things on the right.
It wasn't
Um,
quite what I came up with, I don't think.
But yeah, I don't think I want to come up with this. I think I want.
I think
Yeah, because after C, you would want to do the middle. So you do.
I mean,
So you do C and then,
and then, wait,
Wait.
what? I came up with a much prettier looking tree than that. Just
Yeah?
take a gander at
Here,
my homework. I mean, I put the thing there with the drawing, so.
probably
here's the one I'm picking on anyway.
Oh.
Yeah, this is what we started with. Right, so just taking the half points from each side.
Oh, yeah, I guess it does look. I guess it does look. It doesn't look as nice for this now for some reason.
That's the way I drew it. So the left and right subtrees have the same height, so that's good. So all we need is to know that this is balanced and that this is balanced. And to see that this is balanced, we need that the left subtree and right subtree have the same height, which they do in this case, or within 1. And this has to be balanced and this has to be balanced, and that will be the case. Because here the left subtree has a length of a height of 1, the right subtree has a height of 0. That's close enough. This is balanced and the empty tree is balanced. So yeah, that is balanced.
Okay, cool.
So that's the way you do it.
So there is an actual algorithmic way to do this, though, right?
There's an algorithmic way to do it, and the algorithms that we'll talk about next term allow you to rebalance each time that you add something to the tree. So you start off with an empty tree, it's balanced, you add a node, it's still balanced, you add a second node, it's balanced, you add a third one, and if it's unbalanced at that point, you can make an adjustment.
So is there a different way for this tree to be balanced specifically?
Probably, but I haven't tried putting this data in and using one of the balance algorithms to see what we
Because
come
I'm
up
curious
with.
what it would look like.
I think if you swap A and B, D and E, H and G, and W and Z, those 2 with each other, so instead of AB, it would be BA, and instead of DE, it would be ED. The order would be swapped around and they branch out. So put A there, and then toss it in B would go there, and then you swap out D and E for each other.
Even without swapping D and E, is this still balanced?
Yeah.
Yes, so in terms of the height, it's still
Right,
balanced.
yeah, that'll still be balanced.
So there's a bunch of permutations
Yeah.
right there.
Yeah.
So if we bring in our first node, then we bring in our second, then we bring in our third, we detect that that's unbalanced, we do what's called a rotation. And in this case, the rotation is basically bring B up to the root, bring C down, and it would turn our tree into this.
Okay.
And each time that you add or remove something, you need to do 1, possibly 2 rotations to restore balance.
How does our original tree turn into?
Yeah, that's what I'm curious. It's like, how would you do the rotation with the original tree to get to this?
I don't know how to do it starting with the original tree. We could do it adding 1 node at a time.
No, I mean
But
the original sequence of things. The very, very first thing we started with in the top left. The
Yeah, so I got-
WB.
Basically,
That's what I meant too.
you'll
You
compare
start
the
with
heights
that.
every time, and if they're different more than 2, you do a certain kind of rotation depending on where the nodes are positioned.
yeah, so here I think we're still balanced, and then when we add our G, we find an unbalance over here, and this might be a double rotation, because we're heavy to the right, we're heavy to the left and then to the right. And depending on whether you're left,
Are you
right,
gonna
right,
rotate W to the root then at that point?
You
No,
rotate
you rotate
the
WEG.
twice.
you rotate this one up here, and then you rotate one up there, and that might put W.
You rotate the G where W
You might put
should
G
be.
on the root.
No, I think you just...
Put G where W is.
No, because you do it based off the
W on
deepest
other side.
violation, so you rotate from the W, so you rotate the G up to the W.
Yeah.
And the W goes on the side.
So it becomes G, E, W.
But wasn't that balanced at that point?
At that point, it will be balanced.
The idea is after you do your sequence of rotations, it's going to be balanced.
Yeah. And your sequence is either 1 or 2 rotations. And there's an algorithmic way to decide what you have to do to restore balance based on basically the differences in the height between the left and right subtree at each node. So you measure a balance factor. If it's got an absolute value bigger than 1, it's unbalanced. And starting at the deepest one, you apply 1 to 2 rotations. We'll go through it in gory detail in about 10 weeks.
And you call this rotations? Is that?
Yeah. And we'll probably code it up this next term. I normally don't have people code it, but people will be able to handle it. All right, recursion tree, any issues with that? For Fibonacci, we did it for a smaller Fibonacci number.
Not after the class yesterday.
My only problem was space on the paper.
Yes.
Yeah.
Yeah, a wide piece of paper turned sideways.
I kept having to get rid of it and start over because I wasn't organizing my numbers properly.
Yeah.
My question is, when we did it in class, we did it for Fibonacci 4, which is supposed to be number 5, right?
Yeah.
Because you gave us the sequence 3, 5, 8. Okay, so one.
Toss more numbers in.
Yeah.
So it's the Fibonacci level is not the actual value of the Fibonacci number. That's what I was asking.
So I wanted you to show me the Fibonacci number 21, how you would compute that recursively. And I called that the 8th number, and I said Fibonacci 1 and 2 are both equal to 1.
Yeah, so we start 21, we need
Between the 13 and
13 and 8.
13 and 8.
And then we break those into their
Each one.
ones.
And the
So
13 would be
13
8 and 5.
is 8 and 5.
The 8 would be 5 and
This is
3.
5 and 3.
The 5 would be 3 and 2.
This is 3
Yeah.
and 2.
I found it
This is
easiest.
2 and 1. This is 1 and 1.
And then you go back up.
1 and 1. 2 and 1. 1 and 1. 3 and 2. 2 and 1. 1 and 1. 1 and 1. And then the same thing over here is going to look just like this.
Yeah, I found it easiest to put the larger number on the left and then do the larger number on the left. Just keep going all the way down until I hit 1, branching off, and then go back up. Like
Yeah.
I just did.
And if you're really bored and you have a container of paste and a Xerox machine and a paper cutter, you can do this really easily. Because you just do this, and then you make a bunch of copies of it and cut it out.
Right.
Paste it in under all your 3s.
Or digitally.
Yeah, well, that's no fun. You can't smear bits on your hand and peel it off, right?
Did you want us to do a tree that was like the Fibonacci number with the sums?
I'm interested in the tree structure. I would probably do it like this.
Okay, that's what I did. So
Yeah. Because that shows you how you're actually doing these calls and what you're passing to it. But it's the same tree structure, it's just different labels.
I did that, I got all the way down to the bottom and filled in the ones and
Cool.
this equals this and
Nice.
Is there like a convention on which is the low tree, like low branch, which is high branch, or is that as long as you stay in the same way?
What do you mean low branch versus high branch?
Well, I guess in this case it wouldn't matter. It's like F7, F6. Wouldn't it be the other way around? There's no reason.
Oh, you mean do I do 6 and 7 or 7 and 6?
Yeah,
Doesn't really make any difference.
just as long as you keep the order.
It really depends on how your code is written. If you're intending this to trace your call's behavior, if I say return f of n minus 1 plus f of n minus 2, I don't know which one of those the compiler is going to call first. It may call n minus 2 first, actually. Depends how it's converted into assembly language. But if you really wanted us to mimic what the calling order is going to be and you're reading from left to right, you have to figure out which one gets done first. But the essential information capture here is basically what calls what, right? So in order to compute this Fibonacci number, I have to call both of these, and in order to do those, I have to call these and these. And it's a quick visual view of the growth of the problem.
If you look at how we've done all the other trees, you probably would put F6 on the left side.
Yeah.
Because it's smaller.
Smaller,
True.
yeah.
But they're both smaller than F of 8, which actually tripped me up at first.
Yeah. Let me boot a laptop. Just because we're talking about this. So then we talked about number 3 already.
Yeah, I think that's all the homework. So
What?
that's all the homework.
That's all the homework.
It was short but sweet this time.
Yeah.
Yeah, I like.
Homework's always sweet. It's not always short. So just for fun, I lost my network connection. Go to my phone. I really lost my network connection. What part of connect automatically didn't it get? I don't know.
You know, you can do a curl script that'll sign into the web page automatically.
I would never do that.
Never in a million years.
As he says, as he just starts working with it.
No, I was already connected.
Uh-huh. Yeah.
I don't, because then I have my password. So here's a great little recursive function. This is called Ackerman's function. This is really fun to play with. So a is a function of 2 integers, am plus n. If m is 0, it's just n plus 1. If n is 1, it's am minus 1, 1. Otherwise, it's am minus 1, comma, am, comma, n minus 1. And it's very recursive. And so they point out here Ackerman's function of 4 comma 2 has almost 20,000 digits in its value. This thing grows fiercely. And it's a fun way to motivate recursive functions, because I don't think you can calculate this thing non-recursively. Well, I think you can, but we don't. But it's very easy to write a recursive function for this. But for all but the most trivial values, it blows up really quickly. So,
I was gonna say, oh, let's give it a shot for small numbers, but it's like, oh, 4-2 makes it
Huge.
20,000
Yeah.
digits long.
so if you want to dig deeper on recursion, go ahead and wiki that. And it's got all these cool properties. But yeah, and then we get into the up arrow notation. So I mentioned yesterday that the science of large numbers gets really interesting. So you can start looking at some of these different notations beyond weighted positional notation, simple exponents, to try to capture really big numbers. And this is one place where you start to see this. So, I mean, it starts off innocently enough, and then it just starts exploding. And so these are 2 to the 2 to the 2 to the 2 to the kinds of notations. Yeah, so that's a fun function.
Are those up arrows supposed to be powers?
I think up arrow is like 2 to the 2 to the 2. It's like the number of times that you raise something.
That's interesting notation.
Yeah, I think that's what they call
Noose up arrow.
Noose up arrow.
Yeah. It is found in definition of properties.
Further.
There it is. Noose up arrow notation.
It doesn't. Well, yeah, that's for the link tree. So could you say that 2 to the 2 is 2 up arrow 2?
Something like
Well, I
that.
think it's like 3 or more is what it looks like.
So A up arrow B is A to the B. A up arrow B is B copies of A to the A.
I would say that this makes sense simply because you don't want to write A to the B to the B to the B to
Yeah.
the B because you're going to have not subscripts but superscripts, and those are going to get tinier every time you do it. So that's
Oh,
not a
I
good
see.
idea.
Okay, so 4 up arrow 3 is 4 to the 4th, like 3 times.
Yeah. So 3 up arrow 5 is a succinct way of writing 3 to the 7 to the ridiculous number.
I'm sorry, did they put the superscript 3 before the 4?
That's another way to write up arrow notation, I guess. For double up arrow.
That's weird.
Just in case you really want to screw with someone.
Yeah.
Just write it like that.
If you don't like drawing arrows.
No.
So yeah, that's an interesting area to explore. And then there's Graham's number, which cannot be written with any small number of Knuth arrows.
Any small number of Knuth arrows. Can we like say that it uses some Knuth arrow number of Knuth arrows, or is that just
Possibly.
going too far?
Too far for this class. Yeah, so good things to play around with. None of which help us with graphs, unfortunately, but are still good stuff. All right, so any other questions? We ready to go back to graphs? All right, so I mentioned adjacency and incidence, right? 2 vertices are adjacent if they're connected by an edge. An edge that connects a vertex, we say that edge is incident to the vertex. And we're going to use that eventually to talk about how to deal with graphs inside a program. So the degree of a vertex V is the number of edges incident to it. As usual, in a graph, G equals V comma E, et cetera, et cetera. I'm going to say in an undirected graph, so there's a graph. Degree of A is what? It's just 1. Degree of B is just 1. What's the degree of C? That's 4. Degree of D is 2, and degree of E is 2. So it's just the number of edges incident to a vertex. If you add up the degrees of all your vertices, in this case we get the number 10, and the number of edges is 5, which is exactly half of 10. And that's always going to happen. So the sum of the degrees of all vertices is always twice the number of edges.
Makes sense.
If an edge is going back to the same vertex, is that 2?
That should be 2. So degree is 2, and number of edges is 1.
Very similar to degree.
So you would say that
So there the degree is 3, plus 1 is 4, the number of edges is 2.
it's kind of weird to say that the number of edges incident to it is 2, which is just the one edge.
There we go.
Fair enough.
It's not weird anymore. Yeah.
Is that a symbol for agree, or is it just writing?
I keep wanting to write the hunchback D. It's not a hunchback D, that's a hunchback A. That thing.
Oh.
Partial derivative symbol.
Is it that, or is it?
I think it's that, but I don't know if I can swear to that. But if you want to use it, that's fine. I like drawing them.
Going to the text, yes.
Okay, let us know. So can we prove this? This little factoid that the sum of the degrees is always twice the number of edges?
Sure. Each edge touches 2 points.
Yeah, each edge touches 2 points, which increases the degree of those 2 points by 1. How do we turn that into a formal proof? I already heard it over there.
It sounds inductive.
Induction, right?
It's always induction.
It's always induction.
You know induction, or we'll talk about it in
Yeah.
2.
I think the funniest thing about this class is that anywhere else you go, if you go online and you're trying to learn how to program or something, you're going to hear from everybody that recursion is really hard. Doing recursion is hard stuff, and it's so confusing, and our brains aren't built for it, and nobody here has a problem with recursion. Everybody's just throwing it out there. But induction is the hard thing.
That's good to know.
It's just adding 1.
Yeah.
And I've been thinking that maybe the reason for that is if you're a self-taught programmer who's coming at it from the idea of like learning the language and then figuring out everything else, versus like if you're coming up through it from the mathematical sense as well,
Right.
maybe some stuff like recursion is easier to get, and some other stuff might be harder.
Right.
Yeah.
You know,
Yeah, that makes sense.
because you have just this certain base that you can draw from.
Mm-hmm.
Yeah.
That makes sense.
Because that's also, I always heard, recursive programming is the worst, and it seems like the easiest thing in the world. Like, I don't know.
That's really awesome to hear.
Yeah. Just
Because that's 222, right?
Yeah.
And if you're not getting badly tripped up by recursion, 222 is a lot of fun.
yeah. Because
Right?
it
'Cause
seems
you're
very
actually working
intuitive.
with these cool things. That's great.
Maybe that's from learning induction first. I don't know.
Yeah, the book doesn't seem to give us a multi-degree.
Okay. We can invent one.
Uh-oh.
Uh-oh.
Look at math,
There, we'll do the smiley face.
Yeah.
There's our degree symbol.
That's not
No,
in math.
no,
I know
no,
I
no.
can't.
We're gonna have emoji.
Make a smiley face, but with the thermometer sticking out like it's taking its temperature.
Ooh. There you go.
Yeah.
Pretty good.
By degree, that's
And then every paper you write takes forever. Keep turning this little tiny thermometer.
What?
Number of vertices with odd degree is even.
Oh, okay. Sorry, your handwriting
Yeah,
kind
looks
of
like ever.
died there.
So in an undirected graph, the number of vertices with an odd degree has got to be even. For example, 1, 2, those are the only vertices with odd degree. This has even degree 4, 2, 2. We've got 2 of them. 2 is an even number. Can we prove that without induction?
Without induction, how else are we supposed to?
The only other way we've learned to prove things.
contradiction.
No, better than that. Modulo arithmetic.
Oh, okay.
Yeah.
Because if we have,
It has to be divisible by 2, right?
it has to be divisible by 2, because if you add up the degree of all your vertices, the even ones are 2 times degree 1, 2 times degree 2, 2 times degree 3, and the odd ones are, so these are the even degrees, so they're all 2 times something. The odd degrees are odd numbers. And we know that when we add this up, we're going to get 2 times the number of edges. That's an even number. So the only way that the sum of all of this can be even is if the sum of all your odd degrees is even. And if you add an odd number of odd numbers, you get an odd. And you can show that with modulo arithmetic pretty easily.
Basing this on a theorem that we haven't proven though.
We haven't proven.
Like, are you going to use this then to prove the double thing? 'Cause you just use the double thing to prove
You just
this
use the
one.
double thing to prove
Yeah.
this.
You can't do that.
Double thing you can prove with induction. So start off with a base case of no vertices, or 2 vertices, or 1 vertice, and just keep adding edges and show that it applies as you increase the number of edges by 1. So yeah, this can only be even if you have an even number of those. So that theorem falls out pretty quickly. All right, so we'll start with degree of edges for directed graphs tomorrow, and we'll have positive and negative degrees, and we'll see some properties of that, and then we'll move on to adjacency list, incidence matrices for representing. We'll talk about isomorphisms of graphs to tell when 2 graphs are the same. We'll talk about Euler paths and Hamiltonian paths, a few applications, traveling salesperson, Dijkstra's algorithm, and that should take us through the end of Friday. And then we'll do something short next week, and we'll do languages and grammars for the rest of the course. Cool.
I can't believe we're already talking about rapid recording.
Yeah, it's wrapping up. All right, I gotta scoot to my car. I'll be back.
You gonna turn off the camera?
Oh, thank you. Empty room for 10 minutes.